Hi, I'm Miriam Lowery, and this is Lab 4 Oscillations for Physics 2211 at Georgia Tech. The purpose of this lab is to observe and measure the motion of a mass swinging in an arc while oscillating on a string. This motion was analyzed using tracker, and a computational model was used to predict the object's motion and plot predicted changes in energy. The overall goal of this lab is to determine if the model system satisfies the energy principle. In the end, the total change in energy of the system remains equal to zero, meaning the energy principle is satisfied. The fundamental principles used in this lab are Newton's second law, which states that net force is equal to change in momentum over time, and net force is equal to the spring force plus gravitational force. The other principle I used was the energy principle, which states that the change in energy of the system equals the work of the surroundings plus Q. In order to satisfy the energy principle in this lab, there should be no change in total energy of the system. Therefore, change in kinetic energy plus change in spring potential plus change in gravitational potential should be equal to zero. These general concepts are demonstrated in the diagram. In addition to these general concepts, the formulas listed are also used. First, we'll start with the observed model. Here is my video analysis of the mass's motion in tracker. As you can see, there's oscillation in both the x and y direction. The mass of the object is equal to 0.402 kilograms, and the initial velocity is 0 meters per second because it starts from rest. Some calculations using the observed data were required to get the initial conditions needed for the computational model. First, I had to calculate the period of oscillation for the y direction. I did so by dividing the amount of time it took to complete 3 total oscillations by 3, which came out to be 1.5237 seconds. This value was then used to calculate the spring stiffness K, which ended up being 6.83 newtons per meter. Using this value and the stretched length of the spring, I was able to determine the relaxed length of the spring to be 0.1232 meters. This value will be utilized in the computational model. Moving on to the computational model, I started by setting up my code. First, I defined the initial conditions, which were measured and calculated using the observed data. Then, I calculated the stretch of the spring by subtracting the relaxed length from the magnitude of the spring's current length. I then used the equations for kinetic energy, gravitational potential energy, and spring potential energy to define all of the system energies. These are then added together to compute the initial energy of the system. Then I used the equations for gravitational force and spring force to compute the net force of the mass at each time step. This value is then used to update velocity and thus position. Lastly, the final energy of the system was computed at each time step, and the change of energy was calculated by subtracting initial total from the final total energy. This is what the code looked like when I ran it. For both the x and y directions, the observed motion follows roughly the same pattern as the predicted motion. At later time values, the position of the observed data begins to deviate more from the predicted model. This may be because the oscillation period was calculated using data for the y direction, which may not accurately capture the oscillation in the x. The motion between the observed and predicted in the y direction lines up pretty well, but the predicted data overpredicts the maximums and underpredicts the minimums. This might be accounted for by the fact that the system was not actually a closed system, and there were other things like air resistance and drag acting on the mass that were not accounted for in the predicted model. Looking at the change in energy graph, you can see the changes in gravitational potential energy and spring potential energy oscillate with the same period as the position of the mass changes. When spring potential energy increases, gravitational potential energy decreases, and vice versa. The change in kinetic energy is both positive and negative because the mass gains and loses kinetic energy, with the kinetic energy change being equal but opposite to the total change in potential energy. This means that some of these energies always remain at zero. These observations lead to the conclusion that the energy principle is indeed satisfied. To satisfy the energy principle, the change in energy must be equal to the work done by the surroundings. Since there is nothing acting on the closed model system, the change in energy must be equal to zero. In the graph, delta E remains constant at zero, and this is because the kinetic energy is equal but opposite to the total potential energy of the system. Here I'm comparing the oscillation periods between the x direction and y direction. For both directions, I calculated the oscillation period the same way. I found the amount of time it takes to complete 3 total oscillations and divided that value by 3 to get the total oscillation period. As you can see, the oscillation periods differ between the x and y components. This means that you will end up with a different spring constant depending on which oscillation period you use. This difference will lead to lots of deviations since the spring constant alters the spring force calculated, and this will in turn have a domino effect on other values, including net force, velocity, position, and kinetic energy.